So we now know how to recognize an oxidation reaction and how to recognize a reduction reaction. So now we have to address the question, what reagent goes above the arrow? What reagent do organic chemists use as an oxidizing agent? So a disclaimer to start. There are many oxidizing agents that have been developed by organic chemists. There are entire books full of them. But for the purpose of this introductory class, we will focus on one in particular. So an oxidizing agent is something that is easy to reduce. So remember, in a redox reaction, something gets oxidized and something gets reduced, and the oxidizing agent is that which gets reduced. So transition metals are especially good at participating in redox reactions because they have multiple stable oxidation states. A high oxidation state transition metal complex in particular is an effective oxidizing agent because it's usually easy thermodynamically to reduce a high oxidation state transition metal complex down to a lower oxidation state complex, especially if they're in the top row of the transition metals. So the most common transition metal oxidant used by organic chemists is chromium-6. So the highest possible oxidation state for any transition metal is its group number, and since chromium is in group 6 of the periodic table, +6 is the highest possible oxidation state for chromium. The most common source of chromium-6 is chromic acid, H2CrO4, and its structure is shown on the screen. Chromic acid is sometimes called the Jones reagent, and oxidations with chromic acid are sometimes called Jones oxidations. Note the structural similarity between chromic acid and sulfuric acid. The only difference is a chromium versus a sulfur, but please do not confuse them. Their function is very different. Okay, we've seen several uses of sulfuric acid, but not as a redox partner. Students tend to get confused and use the wrong one on exams, so I'm giving you fair warning. So let's look at an example. An example is the oxidation of isopropanol with chromic acid up to acetone. Okay, this is a case of a secondary alcohol being oxidized to a ketone. What I would like to do now is go over the detailed mechanism of this reaction. Now, I'm going to tell you up front, this is a difficult mechanism. It's not a mechanism that's all that general, and I don't actually recommend spending a lot of time learning this mechanism. But for people who want to know, how does this reaction happen, I'm going to go through it for you. And you will notice some similarities between the first 3 steps of this mechanism and the formation of a mesylate or tosylate. Okay, so in step 1, the mechanism begins with attack of the nucleophilic OH, lone pair on the oxygen, onto the chromium. We're never going to want to form more than 6 bonds to chromium, so anytime we form a bond to chromium, we need to break a bond to chromium. So in this case, to accommodate the incoming oxygen, we break one of the CrO pi bonds, which should make a lot of sense. Then you end up with a really short-lived Zwitter ionic intermediate with a positive charge on one oxygen and a negative charge on the oxygen bound to chromium. These are not normally good intermediates, but in this case, because there's chromium in there, it can happen for a very short period of time. Then we will have very rapidly a proton transfer from the oxygen of the incoming alcohol to one of the OHs that was on the chromium to make a good leaving group, followed by loss of that leaving group to generate the neutral chromate ester. Okay, we have kicked out water as the leaving group, which as we know is a very good leaving group. The only step of this mechanism that's going to look a little wacky to you now is the last step. But think about this as an elimination and it will actually make sense, except instead of forming a carbon-carbon double bond, we are forming a carbon-oxygen double bond. So water comes in as a Bronsted base, removes the hydrogen on the carbon that needs to be removed in order to make a carbonyl group. Those electrons from the CH bond form the CO double bond, and then you break the oxygen-chromium bond, putting those electrons onto the chromium. So chromium-6 in this case is gaining 2 electrons and being reduced to chromium plus 4, and then one of the chromium-oxygen pi bonds gets broken to make an anion, the chromate anion that goes together with the H3O plus that is generated in the course of this reaction. Okay, so that's the mechanism of the oxidation of a secondary alcohol to a ketone with chromic acid. What about primary alcohols? Well, if a primary alcohol is reacted with chromic acid, you don't get an aldehyde, but rather you get a carboxylic acid. So if you do the analysis, this is an over-oxidation. It's a 4-electron oxidation instead of a 2-electron oxidation. The mechanism of over-oxidation is actually beyond the scope of this lesson. It requires some more understanding of carbonyl chemistry that typically comes in the second semester. But it's a result of the strongly acidic conditions of this reaction in the presence of water. So if you want to oxidize a primary alcohol to an aldehyde, which is a more useful reaction in the context of what we're looking at broadly in this unit. In this unit, we're thinking about solving synthesis problems and forming carbon-carbon bonds using Grignard reagents. Aldehydes will react with Grignard reagents to form carbon-carbon bonds, but carboxylic acids destroy Grignard reagents. So the oxidation of a primary alcohol to a carboxylic acid is not going to be a step in a synthesis in this unit, but the oxidation of a primary alcohol to an aldehyde will most definitely possibly be a step in a synthesis problem, because then you can take that aldehyde and react it with a Grignard reagent and get a secondary alcohol. Okay, so what you need to be able to get the aldehyde is a reagent that is not acidic and can be used in an organic solvent instead of water. Chromic acid is only really soluble in water. What you actually do is you take a solid chromium trioxide, dissolve it in water, and that gives you H2CrO4. For something that's soluble in an organic solvent, we need something with a little more organic spinach on it, so to speak. And the solution that was developed is a rather elegant one, and it's called pyridinium chlorochromate. Pyridinium is the cation, so pyridine is a nitrogen analog of benzene. When it's a weak base. When you protonate it, you get the pyridinium ion, and then chlorochromate is the chromium-containing species, which has a negative charge. This reagent is soluble in dichloromethane, so reactions can be conducted with dichloromethane as a solvent. And this elegant solution was developed by E.J. Corey, the same person who developed the idea of retrosynthetic analysis, for which he won the 1990 Nobel Prize in Chemistry. Corey developed the PCC reagent in 1975. So an example of the use of PCC now would be starting with ethanol, reacting it with PCC and dichloromethane. Instead of getting acetic acid, you now get the acetaldehyde that you would like out of this oxidation reaction. Okay, we've done secondary alcohols, primary alcohols. Well, what about tertiary alcohols? Well, there is very little on this slide because tertiary alcohols cannot be oxidized. And the reason they cannot be oxidized is they do not have a hydrogen to lose from the carbon bound to the OH. If you think back to the mechanism of chromic acid oxidation, then the last step, the water comes in and takes off that hydrogen. Because there is no hydrogen there, they are inert to chromic acid or any other oxidizing agent. Okay, so there's chromium-based oxidations in a nutshell. In the next lesson, we will do a similar analysis of reduction.